All right, physics fans, welcome back for another deep dive. We've got a real head scratcher lined up for you all today.
Yeah, always exciting to see what new puzzles the universe has in store for us.
It's a big one. We're
Eh,
talking about the strong CP problem.
Ah, one of the big mysteries in particle physics. Always a fun one to try and untangle.
And we're going to try and untangle it. We're going to try, with the help of this paper, small instantons and the strong CP problem in composite Higgs models. So, listeners, buckle up. This one is dense, even for us. But thankfully, we've got expert speaker here to break it all down.
Happy to be here, as always.
So let's set the stage. For our listeners who maybe haven't encountered the strong CP problem before, how would you frame it in a nutshell?
Well, I guess the simplest way to put it is it's all about symmetry. Or rather, the lack of it where we expect to see it.
Okay, I'm intrigued. Tell me more.
You see, based on our current understanding of particle physics, there should be a larger difference between matter and antimatter in the universe. A lot more, actually.
Right, because we usually think of them as being like mirror images.
Right, exactly. But the universe throws us a curveball. The measurements we have just don't add up to this big difference. It's way more balanced than we'd expect. And that's the crux of the strong CP problem.
Like the universe is playing a cosmic game of Where's Waldo with this matter-antimatter imbalance.
Well, sort of. It's more like imagine you have a perfectly balanced scale. You put a certain amount of matter on one side and expect to need a very different amount of antimatter on the other side to balance it out. But then when you actually measure it, it turns out you need almost the same amount of both to keep things even. It's that unexpected symmetry that has physicists scratching their heads.
Wow, okay, so that's our starting point. This weird, unexpected symmetry in the universe. And this paper thinks it might have an explanation.
That's right. They're exploring a possible solution using something called composite Higgs models.
Okay, before we get too far, can you give us a quick refresher on what those are, just so everyone's on the same page?
Of course. So in the standard model of particle physics, the Higgs boson is considered a fundamental particle. Indivisible, you know?
Right, like the smallest possible piece of Lego.
Exactly. But composite Higgs models, they propose something really radical. That the Higgs boson might actually be made up of even smaller particles. Like imagine if you took apart that Lego piece and found even tinier Lego pieces inside.
Whoa. So it's like the Higgs boson is more of a tiny assembly kit than a single fundamental piece.
That's a great way to put it. And that's what makes these composite Higgs models so intriguing. They challenge our fundamental understanding of how the universe is put together.
Okay, so we've got these hypothetical tiny particles making up the Higgs, and they might hold the key to understanding this matter-antimatter imbalance.
That's the idea. And this is where things get even wilder, because to understand their solution, we need to talk about instantons.
Instantons. Okay, now you're just messing with me.
I know. I know. It sounds like something out of a sci-fi movie. But in reality, instantons are these incredibly tiny ephemeral fluctuations in space-time, like quantum-level blips that pop in and out of existence. And some physicists believe they might play a role in how particles, even those hypothetical ones making up the Higgs, get their mass.
Okay, so we're going even smaller. We've got these tiny particles making up the Higgs, and now even tinier, fleeting things called instantons that might be influencing them. How do you even begin to study something so infinitesimally small?
Well, it's certainly a challenge, but this paper, they suggest that the key might lie in studying how certain values in these models, things like the strength of forces, actually run.
Run. What do you mean run?
I know it sounds strange, right? It's not like they're lacing up their tiny sneakers.
Right, no marathons for these
Yeah.
particles. So what does running actually mean in this context?
Basically, it means that in the quantum world, the strength of a force isn't always constant. It can actually change depending on the energy involved.
Interesting. So the more energy, the stronger the force.
You got it. Think of it like turning up the volume on a sound system. The higher you crank it, the louder or more intense the sound waves become. In this case, it's the strength of the force that gets turned up at higher energies.
Okay, I kind of get it. High energy, stronger forces. But how does this running connect to these instantons and the whole composite Higgs model thing?
Well, that's where it gets really interesting. The paper focuses on how this running affects two key things. the strong force, which is responsible for holding those quarks together, and the interaction between particles and the Higgs field itself.
Okay, I'm following so far.
And what they're suggesting is that in these composite Higgs models, both of these, the strong force and the Higgs interaction, they actually increase in strength at very, very high energies.
High energies, like in the very early universe, right after the Big Bang.
Exactly.
Yeah.
Those extremely high energy conditions are where these tiny instantons could have a much bigger impact.
Okay, so we've got high energies, strong forces, fleeting instantons. I'm seeing all the pieces, but how do they actually fit together to solve the strong CP problem? That's the million-dollar question, right?
It is, and the paper actually offers not just one, but two potential solutions. The first one, it's a bit of a head-scratcher. It involves the up quark.
The up quark, one of the fundamental building blocks of matter.
The one and only. Now, we usually think of up quarks as having mass, right? It's one of their defining characteristics.
But that's how they contribute to the mass of protons and neutrons and ultimately everything around us.
Exactly. But here's the kicker. This paper suggests that because of this running effect, at those extremely high energies we were talking about, the up quark, well, it might actually become massless.
Whoa, hold on. A massless up quark, isn't that a pretty radical idea?
It is, but that's why this paper is so exciting. Because if, and that's a big if, the up quark is massless at those high energies, it could potentially resolve the strong CP problem in a very elegant way.
Okay, you're going to have to explain this one to me. How does a massless up quark, even at extremely high energies, solve this fundamental imbalance we observe in the universe?
It all boils down to symmetry. See, a massless up quark would introduce a specific type of symmetry into the equations that govern the universe. And this symmetry could naturally explain why we don't see as much CP violation as our current models predict.
So are you saying the universe had this built-in mechanism for balance all along thanks to a massless up quark, but then it just disappeared?
Well, not quite disappeared, but it could have been broken. Imagine it like this. In the very early universe, when energies were incredibly high, this symmetry was intact, and the up quark was massless. But as the universe expanded and cooled down, this symmetry could have been broken, and boom, the up quark gained mass. The CP violation we observe today, that tiny imbalance, would be a remnant, a leftover from that process.
Okay, that's a pretty wild idea.
Yeah.
But wait, you said the paper offers two potential solutions, right? What's the other one?
Ah, yes. The other solution involves a familiar face in the world of theoretical physics, the axion.
The axion, of course. Always a crowd favorite.
Right. It's a popular contender for solving various physics puzzles, including this whole strong CP problem we've been talking about. But what's interesting here in this particular paper is that they suggest that within the framework of these composite Higgs models, the axion, it might be much, much heavier than we previously thought.
A supersized axion. Interesting. I remember from our previous deep dives that finding the axion has been like searching for a cosmic needle in a haystack. Wouldn't a heavier axion be even harder to detect?
You would think so, right? And that's part of what makes this paper's approach so intriguing. They're using this idea of running, how the strength of forces change at high energies, to actually estimate how massive the axion might be in these composite Higgs models.
So instead of just looking for one specific supersized axion, they're considering a whole range of possible masses.
Precisely. Their calculations suggest that depending on how the strong force runs at high energies, the axion could be relatively light, similar to what we've been looking for, or it could be a heavyweight champ. We're talking potentially up to 10 to V.
10 to V. For our listeners who aren't familiar with the lingo, that's 10,000 times heavier than a proton. That's mind-bogglingly massive.
It is, and it really throws a wrench into our conventional thinking about the axion.
So we're left with even more questions than answers.
In a way, yes, but I think that's what makes this research so compelling. It's challenging our assumptions about the universe at its most fundamental level. This paper, with its exploration of instantons, composite Higgs models, and the possibility of a massless up quark, it's really pushing the boundaries of our understanding.
It's almost poetic, like these tiny particles, these instantons and quarks, hold the secrets to the entire universe.
It's incredible, isn't it? And what's even more fascinating is that this research, while deeply rooted in theoretical physics, it might actually have implications that extend far beyond the realm of particle physics.
Okay, now you've really got my attention. What kind of real-world implications are we talking about here?
Well, for starters, if these theories hold up, it could completely revolutionize our understanding of cosmology, how the universe began, how it evolved. Imagine the impact on our models of the Big Bang, the formation of galaxies, all of it.
It's like this one paper has the potential to unravel some of the biggest mysteries in the universe.
Exactly. And it doesn't stop there. This research could also have implications for condensed matter physics, which studies the properties of matter here on Earth. The concepts explored in this paper, particularly those related to symmetry breaking, they might have parallels in how we understand different states of matter, like solids, liquids, even things like superconductors.
It's amazing how these tiny particles, these fundamental building blocks, can have such a massive impact on how we understand the universe, from the grandest scales down to our everyday lives.
Absolutely. It really highlights the interconnectedness of everything in physics and the power of fundamental research. Sometimes, the most profound discoveries, they emerge from exploring these seemingly abstract, even esoteric corners of science.
It reminds me of that quote, "The more I learn, the more I realize how much I don't know." This whole deep dive has been a humbling reminder of just how much more there is out there to discover about our universe and the laws that govern it.
I couldn't agree more. And I have a feeling this paper, with its exploration of instantons, composite Higgs models, and the possibility of a massless up quark, it's just the beginning of a very exciting journey.
Well, there you have it, deep divers.
Hmm.
We've taken a deep dive into the strong CP problem, explored the mind-boggling world of instantons and composite Higgs models, and even entertained the possibility that one of the most fundamental particles in the universe, the up quark, might have a secret massless identity. Whew. It's a lot to wrap your head around.
It certainly makes you appreciate the incredible complexity and wonder of the universe, doesn't it?
It really does. And who knows, maybe someday we'll revisit this topic armed with even more mind-blowing discoveries. But until then, keep those sources coming, and we'll keep diving deep.